Hi, hello. This is part 5 of chapter 3. In here, we are going to focus on wave properties of matter, and specifically, we are going to talk about wave properties of electrons. Let's review what we did in this term so far. So we discussed what is a matter is anything that occupies mass and has volume, and then we defined what is the definition of smallest form of matter, which is an atom. And then we said that atom is actually not the um, atom is not the indivisible. Actually, it is indivisible, but because it contains electrons, protons, and neutrons, but it is the smallest form of matter. And we discussed about how we come up to the structure of atom by the work of J.J. Thomson, Rutherford, and James Chadwick. Then we said that okay, nucleus contains protons and neutrons, and outside of the nucleus there contains electrons. That's all we know so far about the structure of an atom, and we don't actually quite have an idea about where the electrons are until lastly we discussed about Bohr's model, where we discussed that light is actually a wave and a particle, and that particle is coming out because when we heat or give radiation to a matter or specifically an atom, those atom electrons get excited and goes to higher energy states, and they come back to lower energy state because higher energy state is not stable. So when they were coming back, they emit the photons in the form of energy. Okay, so now we already know that photons are traveling like a wave. So if photons are traveling like a wave, according to Bohr's model, if you guys remember, we discussed about those circles outside of the nucleus. People have no clue why we are thinking electrons are surrounding the nucleus in a fixed distance. Why is that? So people have no idea about that. Once the Bohr's model is proposed, about Bohr's model of hydrogen atom that we discussed in the previous video, part 4, people agree that how photons are emitted from the atom and how it is called a particle now and travels like a wave, but people have no explanation saying like why electrons are at fixed distance, because it is a particle, and why it has to be at the fixed distance. So then comes Louis de Broglie, that we are going to talk this topic around. So he said that if the byproduct of emission of energy by electrons from high energy state to low energy state is traveling like a wave, the photon is traveling like a wave, electrons should also be already traveling like a wave. That's what he proposed. And actually, it happened to be quite true. And that's what we are going to discuss in this part and the next part. So now you know that electrons around the nucleus are not at a fixed distance from a nucleus. They were actually traveling like a wave. And in fact, it's not a single electron. It's like, probability of the cloud that we discussed in the latter part. So let's try to make some sense of what I just said, with some examples here to help us. So when we say wave, waves are, goes like this, right? So, but here we are not talking about ocean waves where they go to the shore. Here we are talking about waves circularly goes around a nucleus. So because it has to go in circular fashion, so he said that, it's not a straight line now anymore, right? So if the waves are traveling in a circular fashion, so he proposed that those waves must be in a circular fashion, but not a forbidden wave like this. So you cannot have a cut wave function because that would make the electron crash and destroy the atom. So he said that because they were traveling around the nucleus continuously, they were traveling in the form of wave. And when they were traveling in the form of wave, to maintain their momentum, they would have these nodes to change the direction from one type of wave to another type of wave. And well, if you talk about wave, they have to move around continuously. When they do that, they have to change the directions. And when they do that, they need to go through a phase where we call it as a node. You know, the good example to compare like we have here is the guitar here. So between guitar strings, if you think about it, if you see a guitar string, there will be different strings that are connected at different distances. So one would not have a connection because it is a larger string, so that is one type. And some would have a connection in between, so there is a node where, you know, string cannot travel freely. So the sound has some certain limitations based on how the guitar, you know, built. So another variation is the string can be attached to the guitar board multiple times. So these areas we call them as nodes. Nodes are basically where you cannot find the electron traveling. So the probability of finding an electron is 0. And even the guitar makers also use this term, you know, when they attach the string to the metal, that's what they call node. That's where you doesn't cannot generate any sound from the guitar. So because that, we define it as a node. And here is, you know, some graphical explanations of how node works. When electron travels, it travels in any one of these forms. And all of these are showing is that it has a node in the middle where it is changing direction. So follow this one simply. So blue line is going in, let's say, forward motion. And by changing directions in reverse, you have a pink color wave. So an electron can go in both directions, basically. But only thing you need to know is it will has to have nodes where it will change the directions. All right. So based on his proposal that, you know, electron travels in the form of wave around the nucleus, he come up with a formula to explain how to identify the wavelength of an electron. This equation is for the wavelength of an electron that we are talking about. Lambda is the wavelength associated with the particle, and m is the mass in kilograms, and mu is the velocity. Again, do not confuse one equation with another equation. In the previous lecture, we discussed a equation based on Bohr's model of hydrogen atom on how to calculate the wavelength of a photon. And in fact, we also have the same equation that you could use for the calculating the energy differences between high energy state to low energy state. That equations are for calculating the wavelength of the photon that we discussed previously, that has the constant number of negative 2.18. This equation is to calculate the wavelength of an electron. So please have that clarity in mind. We have now an equation to calculate the wavelength that is traveling around the electron. Or not just an electron, or anything that you could calculate. So let's work on this problem. So it said that calculate the calculate the de Broglie wavelength of the particle in the following two cases. In the first case is 25 grams of bullet traveling at 612 meters per second. Second one is an electron traveling around a nucleus moving at a speed of 63 meters per second. Okay. So it is asking us to calculate the wavelength of a particle. So specifically when de Broglie proposed it is for electrons, and you could also use it to calculate for any other particles, because you're not, and it is not ideal to use it for a photon because photon doesn't have a mass. Photon is massless. That's why mainly this equation is not useful for calculating the wavelength of a photon, but any other particle would have mass. So let's try to work on it, and let me highlight where you need to focus on. So the equation is obviously going to be lambda is equal to h over u, and whenever you use this equation, you need to make sure that you are facilitating the correct unit conversions. Okay, that is very important. So h is the Planck's constant. Planck's constant, common most popular units are joules. Multiplied with the seconds. However, for this particular formula, you have to convert those units into kilograms. And only way you need to do that is, you know, use the other Newton variation joules, meaning kilogram times meter over second square. And if you take that, you would end up with kilogram over meter square over just second, because you already have 1 second, so you cancel one here. So now let's make sure any given units are converted into the same units that we need them to convert it into. So because you have kilogram as the unit for H, the Planck's constant, you need to convert 25 grams into kilograms. So you do that and set up your numbers, H over mass, excuse me, 0.025 kilograms and meters per second speed. It is traveling, so it happened to be that wavelength of that particle is 4.3 times 10 to the power of negative 35. 10 to the power of negative 35. I don't know, it is a couple times larger than a quadrillion that I can say. I don't even have a name for it because that huge number, it is 10 to the power of 35. So what it means is, it's highly impossible for us to see the bullet traveling in its wave motion. It does travel because anything in nature will travel in the form of wave, including us, but we are too larger to observe it. At least for us, we are too larger to observe it. So what it means is you cannot actually see it, but it actually does travel in the form of wave in the bullet. Because it is so minute, it doesn't make any difference to our human eye. Let's work on second problem. So second problem has electron already gave in kilograms. So let's plug in those numbers. So it happened to be that only 1.16 times 10 to the power of negative 5 meters. This number is much more logical for us to measure. 10 to the power of negative 5 is something that we could definitely observe or measure, other than 10 to the power of negative 35. So what we learn is, because we already know that the photon, a byproduct of energy emission by electrons, are traveling like a wave, so does electron, because it is the mother of generating the photons. So because electron is already traveling like a wave, the photons are carrying that nature. Kind of, it is in genes. Think of it as it is in genes for the photons because the mother electron gave it that. I like that explanation. In genes, it is in genes. All right. So some more backup data to support our claim that electron travels in wave. So here are the X-ray diffraction pattern of aluminum foil. So when they have taken the X-ray diffraction, they find that it has the electron cloud around the aluminum nucleus at certain distances, like circular rings. Okay. So it kind of supports like Bohr's model, right? For hydrogen, there are orbits further, just like that. And the electron diffraction pattern of aluminum foil, again, also shows that it does have the electron cloud at variable distances. So there is larger electron cloud and smaller electron cloud. So what it shows that is electron does travel around the nucleus, because the electron density is distributed evenly. It's not like there is a dot standing at one place. So electron cloud is around the nucleus. Traveling is kind of we say chemists kind of deceiving word, because kind of like it stays there rather than travel around. So it's more complicated. I don't want you to make it more complicated for you, but look at this nice GIF image. It is just showing that how electrons travels like wave around, and how the electron cloud changes around the central nucleus. All right. And to finish this lecture, what I have is I have a GIF image to show the professors. I think, let me get their names. I have a book here somewhere. Who worked on it? Who worked on it? This is the experiment set up by, let's see their names again, Clinton Davison and Leston Germer. So those two professors in around 1930s or 1925s set up this experiment where they have a high voltage station connected to a tungsten filament, and they supply lots of energy to this high voltage station tungsten filament, where it started emitting electrons at a high speed, and they emit those electrons to a nickel chloride crystal. So it is a crystal structure, it has a fixed arrangement, so that it's set at, that is connected to a metal and a metal detector for the electron flow. So what happened is, when they flow the electrons into this, when they spot this nickel chloride with bunch of electrons, continuously electrons, so they find that at some angles, the electron voltage read by this detector is increasing. All of a sudden, it is increasing. So what they proposed based on this experimentation is that, because there are some higher peaks than the voltage they supplied, so the reading at the detector is larger than what they supplied. So because it is happening, their explanation is that because electrons that are coming out of this tungsten are hitting this nickel chloride, so because they were magnified by the interference pattern, the combination pattern of the waves, it is showing at the higher voltage. So based on this experiment, they are saying that this interference pattern for the electrons happened because electrons are traveling like a wave, and a wave has this nature of both the constructive interference and destructive interference. So destructive interference is where they never detect any flow of current, which means they got interacted at the wrong place and electricity got killed. But constructive interference is when electrons that are traveling in wave combine to form larger wave, thus read the higher voltage here. So based on this experiment, they conclusively able to confirm that electrons do travel like a wave. And other than this, I also have a video to show you. I think he's a fantastic professor. So I'm going to talk less until we finish this video. Let me fast forward this video to where
which is an evacuated glass tube, and in it is an electron gun. So you can have a look at that if you want to remember how the electron gun works. But the one change we've got here is, in front of the electron gun, I've got a sample holder, and inside that is a very, very thin piece of graphite. Now, what that is a series of atoms of carbon regularly arranged in a lattice or in a crystal. And what we're going to do is fire individual electrons at that crystal lattice and see what happens on the fluorescent screen of the tube. So let's see if we can guess what happens first. Electrons we imagine as particles, and we can imagine the graphite crystal as being a series of atoms separated. In fact, a better model might be a crisscross shape like this. So if we were to fire individual electron particles at this, we'd expect them to go through the gaps, and when they hit the atoms, to not go through. So I suppose what we'd expect is a speckly pattern of dots all over the screen, with individual electrons going through each gap in the crystal lattice. So let's get our electron gun working and fire high energy electrons into the graphite sample. So 6.3 volts into the heater, and all that does is produce a source of electrons. Let's force them off the heater by making it very, very negative, so minus 5,000 volts. And let's make the front of the electron gun, the anode, very positive, and that goes into the positive terminal of the power supply. I can see the filament glowing already, so all we've got to do to accelerate the electrons through the electron gun is turn up the anode voltage. And what we're going to do in a second is switch the lights off in the room, and I'm going to turn the screen to face you, and let's see what image we get on the screen. So I've got the screen facing you. Let's turn up the accelerating voltage, and let's see what we get. And what we get on the screen is absolutely remarkable. It's not what we expected at all. We thought we'd get lots of dots as the electron particles went through gaps in the atoms. But instead, what you see is a series of rings. And if you look at them crosswise, they're bright in the middle, then dark, then bright, then dark, going out both sides from the central dot. And this should remind you of diffraction and interference patterns, where you get bright and dark fringes. But hang on, that only works with waves. So what you're seeing here is really bizarre, that we're getting an interference or diffraction pattern. And what's happening is the electrons are passing through the gaps in the atoms, and they're diffracting and interfering with each other. In other words, they're behaving like waves. So hang on, what is it now? Is an electron a particle, or is an electron a wave? And what you might know of quantum physics is that we have the concept of wave-particle duality. And this experiment can only be explained in terms of electrons being waves. So this is a very odd effect indeed. Electrons are behaving like waves and causing a diffraction pattern on the front of the tube. This idea was first suggested by a very young man called Louis de Broglie, who was a member of the French nobility, and he did it in his PhD thesis in 1924. It had not yet been observed, and it wasn't until 1927 that the effect of particle diffraction and interference was observed, and in 1929 he rightly got a Nobel Prize for this. So now for the tough explanation. If you remember, our electron gun had 5,000 volts across it, so it gave the electrons 5,000 electron volts of kinetic energy. If they've got kinetic energy, and they indeed have a mass, then they have momentum. And what Louis de Broglie said is that particles that have momentum will also have a wave-like property. They will have an associated wavelength. And that wavelength is equal to the Planck's constant h divided by the momentum, mv. So you can imagine particle electrons with their mass having a momentum, mv, mass times velocity, hitting the graphite sample, behaving like waves, and producing a diffraction pattern that allows us to back calculate from their wavelength the spacing between the atoms. And we get about 1 × 10⁻10 meters. So a quick recap. If you remember, the electron gun had a graphite sample in front of it, and that graphite behaves like a crisscross grill. So the electrons go through the grill, diffract, and what you see on the screen is the interference pattern of those diffracting electrons. There is no way we could get this image on the screen if electrons were behaving like particles. They must be diffracting, and therefore electrons must be behaving like waves. So you've seen wave-particle duality in my videos now. You've seen electrons behaving like particles, and today we see electrons behaving like waves. Bit of an A-level experiment, that one, but a really interesting one and a good introduction to some quantum.
I got to admit, he has done far better job than me explaining this topic with the experiment and also his fantastic words. Kudos to him. What a nice job. What a fantastic video. I hope that my little bit effort and the physics teacher probably from Europe, Anthony Francis Jones, efforts that you learn that electron also travels in the form of wave, and you could actually calculate its wavelength if you know the mass of it, and also you can calculate the wavelength of any other particle. That's all for this lecture. I'll see you again in another lecture of this chapter.